Hello, good evening. My name is Vivek Singhal. I'm a co-founder and data scientist at CellStrat. We are an AI startup here in Bengaluru, India. I welcome folks from all over the world to this webinar. Let's get going. Let me just discuss a few logistics items here just to help you out. So I hope you can hear me clearly, and I hope you can see my screen. If you cannot see my screen or if you cannot hear me clearly, please raise your hand in the chat window and we'll try to address the technical problem. If not, we'll begin. And if you have any questions around the content, you can put them in the chat window. We'll try to take them towards the end because we have a lot of content to cover. This webinar is being recorded. After the end of this webinar, we'll put this on our YouTube channel so you can also see it offline or share it with your friends. Okay, so let me just begin here. In case you have any technical difficulty, just raise your hand and we'll try to address it. So today we'll be discussing the second webinar in our series of machine learning. We started last week with introduction to AI and machine learning. And today we'll discuss types of machine learning. So, all right, let me keep going here. So just a brief plug on my startup. I am a co-founder. We run CellStrat. We are an AI startup involved in training, evangelism, and product development in AI and deep learning space. We are very passionate and excited about artificial intelligence and what all it offers. And we can clearly see the global technology leaders talking about this area is revolutionary. And folks have said statements like AI is the new electricity. So it gels with what we think about it, and we are very excited to be in this area. And I'm excited to discuss with you all innovations in AI, machine learning, and deep learning. Okay. So let's just quickly define AI and ML, even though we did it in the last session, last week. As we discussed before, AI is trying to make machines intelligent and simulating human intelligence. Okay. So humans are said to be intelligent. They can do complex information processing and take decisions based on information presented to them. Similarly, we are trying to inculcate or incorporate intelligence in machines, and that's why we call it artificial intelligence, because it's not real human intelligence, it's artificial after all. Okay, so that's what we refer to as AI or artificial intelligence. Now, machine learning is a very major branch of AI. What this means is that this is the technique by which we make machines intelligent. And the way we train these machines is by making them learn from data. So AI and machine learning feeds off data. So by observing the environmental data, given certain circumstances or input variables, something is happening, or some inference is being derived. And this kind of input and output, once we feed into a machine, it starts learning from data and it is able to derive, an ability to predict the output after seeing the input. Very similar to how human mind works. All right. And so lots of examples of AI and machine learning. For example, robotics, the entire field of robotics, computer vision, image processing, chatbots, NLP, you name it. I mean, the list is extremely infinite. And that's why you hear so much chatter about AI and machine learning all over nowadays. And because the applications are quite remarkable and they are in almost every sector as we know it. Okay, so I'll just keep moving here. So machine learning, we already said, this is where we build algorithms that allow computers to learn to perform tasks as opposed to being explicitly programmed. So we are basically training machine learning models which observe current data and are able to derive, predictive analytics and able to use these ML models to predict output for new kinds of input. So we are training machines to learn from data. That's what we are doing with AI. And a machine learning is a technique which facilitates that by making the machines learn by observing current data. Okay. And so we saw an example of this when way back in 1997, when IBM supercomputer called Deep Blue beat the reigning chess champion from Russia at that time, Garry Kasparov. And Garry Kasparov wrote a very emotional book about the concept of AI after his defeat by the IBM supercomputer. And more recently, we have read about Google's AI division, which is called DeepMind, created a software called AlphaGo, which beat the reigning global Go champion. Now, this Go is a game played in Southeast Asia, not so much in US or India, I believe. And so this software from Google uh, was able to beat the reigning Go champion by name of KG of China, as well as Korean champion Lee Sedol. Just one note, please. I am in an apartment where there are thunderstorms nearby, so probably you'll hear that in the background. So I hope that's not too much of a bother. We'll keep going. Can't do much about it. Um, so as we were saying, Google DeepMind has created a game called AlphaGo, which is able to beat the reigning Go champion, and this is a very complex game to play even for humans. So now they have a machine and a software which is able to master this game and beat the global champion. Okay, we'll keep going. So we talked about machine learning, So what are some of its key aspects? So one is it's very computing intensive. It needs millions of computation cycles typically. That's why typically it's hard to do on small desktop computers. You need cloud and server capability to be able to do machine learning. And it often involves retraining if you will. And just give me a moment. I'll try to shut my window if that helps. Just a moment. Okay, there. I just shut my window, hoping I can drown out the thunderstorm noise. Certain things are still not in the control of AI, I suppose. Okay, with that note, so, as we were saying, machine learning sometimes involves repeated retraining, where it has to, when it is not able to learn properly and it doesn't pass the validation test. So we'll have it retrained, in that sense. And it does need a lot of training data. So to do accurate training and to do accurate model prediction, it needs a lot of training data typically. So that is one of the banes of machine learning in AI. Unless we have a lot of data, it's generally hard to train good AI. Okay. And as data gets added, ML training can learn incrementally. So it need not learn in a batch mode. It can also be made to learn incrementally. Okay. For example, when we are doing a natural language processing or NLP application, it can pick up new learning from new spam words or new kinds of speech which comes through. Okay. Okay. Now let's look at types of machine learning, the main topic for today. So there are two major categories or types of machine learning, and we call it supervised and unsupervised learning. So what is meant by supervised learning? Supervised learning happens when program learns from training data. That means you can see in the infographic there at the bottom. So I am given lots of training data samples of the kind x1, y1, x2, y2, x3, y3, and so on. So x is an input variable and y is the output variable. Let's say I'm given 1,000 of these samples, so I'll have up to x 1,000, y 1,000. So for each training input value x1, I know the corresponding output value y1. So let's consider this as historical data. We also call it labeled data. Labeled data means that the output y is known for that input x. Okay, so this is historical existing available data, also called labeled data. Now we feed this into the machine learning model, and it is able to infer or derive a function, and the function may have the form y is equal to some function of x. Okay, y is equal to some function of x, and then we apply this kind of relation to future input. So for any x new, any new value of x input data sample, any new input data sample, I'll be able to predict y using this equation. This is exactly what supervised machine learning means. By observing current labeled data, it is able to infer or derive a function and then use that for future predictive analytics. Okay, let's keep going here. So this slide shows an example of what we just discussed. So here I am showing 10 samples, 10 data samples. So for every input X, I have an output Y, and we call that the label for the output. Okay. And then we train the model or train the algorithm. Basically, when we say train the model, what we are trying to do is it is the program is trying to reverse engineer the relationship between X and Y. By observing these XY data samples, it is trying to infer, derive, or reverse engineer the relationship between X and Y. And when it learns that algorithm, let's assume it has that form which is shown there, y is equal to some function of x. For example, 5x1 plus 3x2 square plus 54. It could be anything, right? And then we deploy that algorithm in production, and that is called a learned machine learning model. Of course, it is fully trained model. And then for any new input x new, I am able to use this equation to predict the output y, because I already know the relationship between x and y, right? So this is exactly what is happening. Now in the traditional analytics world, you would have to hard code this equation in the program. It's not learning from data. So the critical difference from traditional data analytics and machine learning is, here I am learning from data. Here the program is learning from existing input and output data. Whereas in the traditional data analytics, that algorithm would be hard coded by the programmer. And so that means the algorithm would have to be known to the programmer beforehand, right? Here, the model is actually learning the equation or that relation between x and y. So that's what makes it intelligent. That's why we do not club data analytics under artificial intelligence, but we put machine learning under artificial intelligence. So because here we are, the model is far more intelligent. Okay, I do have a question here. Uh, I'll just take this question, but normally I like to take the questions in the end, but you can keep putting them in the chat window lest you forget them. So the question is, when I do forecasting, I train data every month. I select new models for forecasting on basis of training. Is this machine learning? When I do forecasting, I train data every month. I select new models for forecasting on basis of training. Uh, well, if you are selecting a certain machine learning algorithm is fine, but if you are hard coding the algorithm in your program, it's not machine learning. It's traditional data analytics. If you're hard coding, the relationship between input and y in your program. So one is programmer driven, equation. The other is the model driven equation. So in machine learning, it is model driven equation. The model reverse engineers or infers the relationship between x and y by observing current data. I hope that is clear. Let me just keep going here. So there are two broad kinds of supervised learning. So again, we distinguish two different kinds of supervised learning. The first one is called classification, and basically we are trying to answer a question: what class? For example, in the chart shown on the right, you can say there are two types of dots: a black dot and white dot, and we are trying to find a classifier which can distinguish between the two dots, black and white. As you can see, there are three possible classifiers which are shown here in different colors. The green one is not good because it did not classify the white and black dots clearly, right? The blue one works, it's fine, but it's too close and there's a chance of error. So the best classifier here is the red line, represented by the H3 line, because it is bang in the middle of black dots and white dots, and it is maximum distance from both sides, so the chance of error is minimized. So the red line is basically what we call a classifier, and this is the red line is what the machine learning model has learned, the equation of that line, and after that, once we know the equation of that line, the model will be able to predict for any new dot whether it should fall to the right or the left of the red line. Okay, so this is how the classifier would help us once deployed in production. This works when the output has finite and discrete values and not continuous number as in case of regression. Now, another example here is that social media sentiment analysis. How is the global economy performing? So people are tweeting about it, let's say. So is the sentiment positive, negative, or neutral? Are we happy about the state of global economy, or are we unhappy, or are we neutral about it, right? So that's positive, negative, or neutral sentiment by the public, let's say in a Twitter feed. So that we would like to classify it into 3 different classes, right? Or learn a classifier. And then the second kind of supervised learning algorithm is regression. So what we are doing here is, here we are given those blue dots which you see in the chart. The blue dots are actually the input, and the red line is the output of the machine learning process. So the endeavor here is for the program to try to decipher or infer the equation of the red line such that it satisfies most of the blue dots to the greatest extent. Now you will notice something here. The red line does not pass through each of the blue dots. So our model is approximately correct. It approximately satisfies most of the blue dots. The red line satisfies the blue dots approximately, not precisely. It's not really practical to have a line pass through every blue dot. It would be a totally zigzag line and not a practical equation we can work with. So we accept a compromise, and we want to find a linear equation. Hopefully, linear means a straight line, which is easier to deal with linear equations and linear lines. And so we are able to find a equation y is equal to wx plus b of the red line, which satisfies the most of the blue dots. And once we know the equation of this line y is equal to wx plus b for any new input x, we'll be able to predict the output y correctly, right? So what we try to learn here, we are essentially trying to learn the value of w and b. W is called what we call weight, and b is called bias. So bias is just the value of the output when x is equal to 0, and weight w is the weighting factor by which the input x is multiplied. So what we are trying to learn here is the ideal value of w and ideal value of b, and the ideal values should be such that this equation satisfies most of the blue dots. Blue dots are the training data provided to us, okay, of x1, y1, x2, y2 format. An example, a relationship between environmental temperature given humidity levels. For example, I want to determine what's the temperature today given the humidity. Are we able to decipher or infer an equation between y and x? Right. So that's what we are trying to do here. Okay. So there are some more questions coming in, but just in interest of time, I'll take them up in the end. Kindly just keep posting your questions in the chat window. Let me move forward here. So now let's look at the second major category of machine learning, which we call as unsupervised learning. In unsupervised learning, what happens that when training data is fed to the algorithm, but not the corresponding label. So this is called non-labeled data. The term we use is non-labeled data, or unlabeled data, whatever you prefer. And here we have just input X, but no corresponding Y. So we cannot do regression or classification with this kind of data, but we can still do something useful with it. For example, we can try to derive clusters. For example, if you are reading a Google news feed, for example, Google is always trying to segment the news feeds into different categories. For example, sports news, political news, or business news. So these, news portals are always trying to segregate the news feeds they are getting from different sources into categories of news, so that users who are interested in sports can directly go to the sports section. Those who are interested in politics can go to the political news section, and so on. So we cannot do classification and regression with unlabeled data, but we can still try to find clusters of similar kind of groupings. So this is called unsupervised learning, and one example of this is clustering, as we just discussed. Okay, and one of the popular techniques we use for clustering is called k-means cluster analysis. Let me keep going here. So this is just showing the clustering which we were discussing just now, that we are given unlabeled data, lots of x values, and we are trying to find or group them into clusters. So on the right, I was able to group them into clusters. So this was unsupervised learning because there was no output y. It was just x, lots of x data samples. One more unsupervised learning technique refers to as visualization. So in visualization, let's say I'm given lots of kinds of data about some kind of moving object, and I'm trying to plot it in a visualization plot and show similar data samples together. So in the visual plot, you can see that the automobiles are shown on one side, the trucking data is shown on one side, the birds are shown together in one side, cats and dogs are segregated as well. So unlabeled, unsupervised data we got, and we were able to visually plot it in such a way that it creates separate groups or clusters, visually speaking. So this is what we call as a visualization, a technique. And in machine learning, often we deal with the word visualization because everything has to be visualized. Without proper visualization, machine learning does not make sense, normally speaking. Okay, and sometimes we want to like to plot this into 2D or 3D visual plots because human eye can only comprehend maximum of 3D, and beyond 3D it can get very difficult to visualize actually. So we try to generally plot a maximum of 3D plot, not more than 3D. Okay, so I'll just keep going here. One more kind of unsupervised learning is when I'm trying to detect anomalies. A very simple example is the credit card statement which we all get, and all of us sometimes are scanning through a credit card statement. We find a transaction which does not seem to follow our usual spending pattern or which we do not recognize. So that transaction we'll call as what we call as anomaly. So we are trying to find anomalies in a set of data, and we don't have any output label on the anomalies, so it is unsupervised learning data. Okay, unsupervised learning is happening. We have to detect anomalies on the fly by observing certain data set. Okay, and this is also an example of unsupervised learning technique. Let me just keep going for now. I understand there are a lot of questions coming. Kindly bear with me. I'll take them up shortly once I'm done with the session, because otherwise I'll run out of time and there's a lot of content to cover. Okay, supervised learning algorithms. There's a nice list of supervised learning algorithms which are shown here. K nearest neighbors, linear regression, logistic regression, support vector machine, and so on. So today I am not going to go through these, but in a subsequent webinars, we are going to cover most of these in sufficient detail. So if you continue to attend our webinars, which happen every Thursday normally, you will be you will be discussing many of these algorithms in sufficient detail. Okay. And this is another list of unsupervised learning algorithms. Again, we will be covering some of these in subsequent webinars because each is a very big topic, and in 1 hour it's not possible to cover a lot more stuff. So now I want to come to the core ML process, particularly as it relates to supervised learning. Supervised learning is the most common form of machine learning. Unsupervised learning is not that mature or technologically feasible yet, because the technology required or the kind of algorithm required for unsupervised learning are still in the works and they are not yet mature. The global data scientists are working on them. Supervised learning is what is highly mature set of algorithms, and so those are the mostly what we do in actual business. And so let's understand the supervised learning machine learning process. So you can see a data set on the left. So it looks like a normal Microsoft Excel file or a CSV file or even an RDBMS table from your Oracle or SQL Server database. There are columns and rows, right? And uh, and then we are trying to train a model. In this case, I'm using something called neural networks, which is an advanced form of deep learning algorithm to train a model, and I'm trying to derive an inference. Okay, so this is essentially what we are doing. Now let me expand this in the next slide. So here I have expanded that ML process, and mark you, we are mark that we are only talking about supervised learning, not unsupervised learning yet. Okay, so there are 4 major steps in this ML process of a supervised learning. The first step is data preparation, and the second is training step. Third is evaluation or test step. The fourth is production deployment. Now this is a really important slide. So because this is how a core ML training process works. So we need to understand this properly. So I'm going to spend a bit of time here. So as you know, in machine learning, data is the most critical first step. So a lot of data scientists spend a good amount of time trying to clean up data and preparing data for machine learning process. So we already discussed that the labeled data may come in the form x1, y1, x2, y2, x3, y3. So one of the things we like to do is clean data, remove incomplete entries or irrelevant entries, right? That's data cleaning process. We also do something called feature engineering. So we say, if I'm trying to do a house price prediction model, for example, and then what are the features or factors which govern house prices in a city? So it may be the square footage of the house, or the the floor of the house. Is it first floor apartment, second floor, or whatnot? It could be distance from the city centers. It could be the quality of the builder. It could be the age of the house. So these are all called features or attributes of the input data. And we do some kind of feature engineering where we try to ascertain what are the most critical features in this problem. All right, that is called feature engineering. And then what we do, we reserve 80% of the available data. Let's say I had 1000 data samples, x comma y data samples. I reserve 80% of those for training step and 20% for evaluation step. Why? It is very similar to a teacher teaching a class. I consider a high school teacher trying to teach a maths class. Out of the 10 problems in the book, the teacher will only teach 8 problems to the student. She will reserve 2 problems for the final exam, because teacher doesn't want to show the all the problems to the kids in case they cram and come prepared with all the problems in the exam. So we keep some data, let's say 20% of the data for test step, and this can be called as evaluation or test data. And during training, we train the model on the train underscore x data set, which is the 80% of the original data. And let's say it is able to derive the relationship between x and y is equal to fx, some function of x. Then we pass that learned algorithm y is equal to fx to the evaluation step, and then we try to test its accuracy. The way we test it is we pass the remaining 20% test data which we had reserved earlier and not used it for training, and we just pass the x test into this and derive y prediction. So whatever y it predicts for the test x values, we compare it with the known y. So I try to compare the predicted value by the algorithm with the known value. So I'll repeat that. So as you know, even for the test data, I knew the correct y, right? It was all labeled training data. But I use the equation which I learned in the training step to try to predict the correct y for the x samples in the test data set. So the predicted, y versus the known y. So I'm comparing predicted y with known y. If they match, that means the algorithm is performing correctly. It is predicting the output as we expect the output to be. If y test and y known are matching, that means it is predicting the output correctly. If they are not matching, that means the algorithm is still not properly trained. It needs to be sent back for training, retraining. So if the accuracy score is less during testing, we send it back for retraining. And obviously we have to change something to try to improve the training step. We have to either give more training data or increase the complexity or the capacity of the algorithm, or completely change the algo. Okay, so we have to change something so that the training is better, and next in the next pass the evaluation. So this kind of repeated retraining happens until and unless the test or evaluation step passes. By passing, I mean that it is able to predict the output as per the known output. Okay, so prediction matches the known output for test samples, and then once it passes the test step, we put it in production and we use it for predicting output y for any new input x. Okay, and some examples of learned algorithm are shown on the bottom right. I hope you understood. If you have any questions, you can put them in the chat window. We'll take them shortly. I'll keep moving now. So just to summarize what we did, we trained a model and it was able to decipher an algorithm, something of the nature y is equal to function of x. And then for any new input x, it is able to predict the correct output y. And we are using the algorithm trained on historical or labeled training data. So just few more critical aspects, then we'll be sort of coming towards the end of the theory part. So we have been talking about different kinds of data. So we want to just get that understanding out of the way, different categories of data. So we have what we call labeled data, where for input X, we know the output Y for the historical data, and typically we'll reserve 80% of this available labeled data for the training step and 20% for the test step, right? And then we have unlabeled data where the output label y is not known and is not marked, in which case it needs unsupervised learning as we discussed before. Okay. Then out of the training data, we had carved out 20% data, which we called as training test data. Sometimes we want yet another test step. So we are not satisfied with the test step. We reserve yet another set of data for the a test over test, if you will, or a super final exam, and we reserve what we call a validation data set. So even though it passes test, but we take it through yet another, unseen data set called validation data set, so that we can retest whether the algorithm is properly trained. Sometimes we are not satisfied with the output of the test step, and we want to test it yet one more time using the validation data set. All right, let me keep going. So we already saw, so if we were to segregate original available data into three data sets, so we could reserve 70% into training data set, 20% for the test data set, and 10% for the validation data set. So this is a very normal or rule of thumb what we use in different machine learning programs, okay? And each data sample is refers to x comma y kind of data sample. Now, one more thing you may want to note here, while I am showing x1, y1, the x could be a set of input factors. For example, it need not be just one input factor. For example, when I'm trying to do house price prediction model, it's not just one thing which influences the house price. It's not just the size of the house, right? Also the age of the house or the distance from city center, or our other neighborhood variables like shopping was nearby. So those factors also are input features or input factors which would influence the house price. So x normally is a set of input variables, and in most cases y is only a singular output. In my house price prediction model, y is the price of the house, and I want to train a model to predict house prices given a set of input features. All right. So x will be many typically, and y will be a singular value normally. Now, during testing the algorithm, some problems can happen. So if the learning is poor, what we have an underfitted situation. Okay. So if we did not have proper, amount of data, we have less data, or some critical features are missing, and the test step is not doing well. So we have an underfitted situation. For example, if I'm trying to do house price prediction model, and I forgot to give the age of the house as well as the size of the house, so I might have an underfitted model because I forgot some critical features. I didn't account for some critical features which also influence the house price. Okay, so the model will be badly trained. It will be called underfitted. And if the training is too intensive, it may lead to the reverse situation, which we refer to as overfitting. Overfitting simply means that data is too tightly trained. Let me give you an example. Again, with the house price example, if I am trying to predict house prices in a city like New Delhi, for example, but the same model may not do so well when tested in, let's say, Mumbai or Kolkata or Chennai or Bengaluru, right? Because we train the model on the Delhi or the New Delhi housing data set. So it will be overfitted to New Delhi housing situation. It will not be probably be able to handle the house price predictions from Mumbai, Bangalore, or Kolkata, right? So this is what we call as overfitted model, where it is overfitted to a limited data set. It has not seen certain other data sets which it will be provided during production. Okay, this is called overfitting. So the how we prevent overfitting, we use a technique called regularization. So what we do, we deliberately introduce errors in the training. So if I am doing a house price prediction model for houses in New Delhi, then I will deliberately introduce an error so that it is not very tightly trained on the New Delhi situation, and it is able to generalize for more kinds of houses in other cities as well. So the technique we use is called regularization, and what we are trying to achieve is a generalized situation. So those are some keywords we use in machine learning. So where as a data scientist, we have to account for all of these nuances during machine learning, and sometimes have to retrain the models to overcome either underfitting or overfitting. Okay. So this slide just shows the three kinds of two extremes which can happen. We may have an underfitted model. You can see the line is not passing the dots very nicely, so it is very approximately correct only, maybe 60-70% correct. And on the right extreme, I have overfitted model, but it's not a practical situation. It cannot adjust to new data samples. There are two different lines which have come out. So in the middle, I have a more appropriate model, and we can call it appropriate capacity or appropriate, appropriate and generalized model. Okay. So we have used regularization to arrive at appropriate capacity. Let me keep going. So this is, I believe, my last slide. So after that, we can take up questions and also see some hands-on tutorials. So when we are discussing overfitting and underfitting, what was happening was that we discussed these terms called bias versus variance. These are important terms in machine learning. What does bias mean? Bias means tendency of a model to learn its around distribution around its average. Okay, and it is not able to do a more extended data set learning. It has low variance, high bias, which means that it is assuming for example, in house price prediction, it is trying to learn more of the center point or the average of all the house prices. So that is the center point is called the bias. So it is too biased towards the center of the range of the house prices, whereas variance is covering a wide range of house prices. So I hope you understood that. Bias is the model is trying to zero in on the average house price for the region, whereas variance is trying to cover a wide gamut, a wide variety of house prices. So high variance means low bias, tightly trained, overfitted. So high variance tends towards overfitting. The model is too tightly trained. It is covering all the samples too closely, and hence it becomes overfitted or tightly trained. And whereas low variance high bias means that it is a simple model, it is trying to zero in towards the average of the output level or average of the house prices, and it is underfitted, not covering the wide variety of data, and it is trying to learn more near the average of the output range. Okay. So we will understand these terms in more detail in subsequent sessions. It's a slightly complicated concept, but it is basically related to underfitting and overfitting. Okay. So let's see some examples of supervised learning. For example, we do chatbots. We are using Amazon Alexa chatbot. We are using Google Assistant chatbot and Apple Siri and Microsoft Cortana. So there is a voice recording. There's an output Y, which is a transcript for the voice recording. And the application we are training is the speech recognition, speech chatbot. And based on historical market data, we are able to predict future market patterns. So all the Wall Street traders are constantly using historical market data to try to learn models which can predict future market data. So to increase their share profits to share trading. So this we use something called trading bots there. Uh, for a photograph in Facebook, where we are trying to Facebook is automatically trying to caption the photograph. So by giving it lots of captioned photographs, it is able to learn to create new captions automatically or new tags automatically for the photograph, right? So image tagging application in Facebook, drug chemical properties and how effective this treatment is for this drug. So it's used in pharmaceutical R&D, and so on. So in the last one, you can see at the bottom, so given a face, I assign a name. So I say a face, I say this is my friend Samir Mathur, and then I am training a face recognition application so that next time the application sees that particular person's face in a photo, it is able to tag that person as Samir Mathur. Okay. So there are so many countless applications where we can use these kind of supervised learning systems. Okay, I told you there's a last slide, but I think there are two, three more. Just bear with me here. So the third category of supervised and unsupervised would be semi-supervised, where part of the training is supervised, part is unsupervised. For example, Google Photos from a trip. It automatically detects the same person in multiple photos. So once I have labeled a person's photo in one of the images, in subsequent images, it will be able to detect the person automatically. So partly it was supervised because I gave a the human being gave a tag or the name to a photo, but in subsequent photos it was able to do automatic detection. So it combines the features of supervised and unsupervised learning. Okay, some examples of this are in deep belief networks and restricted Boltzmann machine. These are advanced deep learning, algorithms, which I cannot discuss in this session, but we'll take up in some other session. So finally, the fourth major kind of learning is reinforcement learning, which is typically used in gaming, robotics, and also driverless cars. So here, what happens is the agent is observing the environment and takes some action. And if the action is a desirable action, the environment gives a reward R to the agent. Okay. So this is what we call as reinforcement learning or rewards-based learning. It is similar to teaching a dog to fetch the ball. If the dog fetches the ball, we will give the dog a cookie. So the dog starts learning that if I continue to fetch the ball, I will keep getting a cookie. So this is exactly how we teach an agent in a rewards-based learning environment. So the agent starts doing correct actions because it is getting some kind of reward tokens. So if it gets reward tokens, it understands that it has to repeat these kind of behavior. And if it does not get the reward, the agent understands this behavior is not desirable because it was not rewarded. And in future, the agent will not repeat that action. Okay. So here we influence agent behavior in a certain direction by giving it rewards for certain desirable actions. This is called reinforcement learning. It's an advanced topic in deep learning. And at some point in our webinars, we'll take this up. It's more of a recent phenomena. Okay, so that brings me to the end of my theory part today. And our next webinar is next Thursday, and we are privileged to have a guest speaker from the company AMD. As you know, AMD, just like Intel, is a leading semiconductor maker in the world, and they have graciously provided us a deep tech scientist, Dr. Prakash Raghavendra from AMD India Bengaluru division, who will be explaining how AMD GPUs can be used for deep learning process. So far, we have heard of NVIDIA GPUs and some other GPUs, but AMD also has a very robust GPU architecture, which is facilitating deep learning applications in TensorFlow and some other tools. Okay, so next Thursday, tune in at 8 p.m. India time, 10:30 a.m. US time to learn about the AMD GPU architecture. So that brings me to the end of the theory part. Let me quickly address some sessions before I go to hands-on tutorials. All right. So what if my data is non-linear? Yes. So if my data is non-linear, we can do things like polynomial regression and some other algorithms are there to handle non-linear data. Not every time the data will be linear. So that is correct. How is regression applied in that case? So it could be polynomial, support vector machine. So there are a lot of algorithms which can deal with linear data. So in fact, in the tutorial, I'll show you a sample of polynomial regression momentarily. Just hold on. Uh, can I get a recording for this session? Yes, we have recorded this session and it will be available on our YouTube channel in a day or two. Is this based on CIFAR 10 data? From what I know, CIFAR 10 is related to driverless cars, and I am frankly not in that area yet, so I cannot comment on CIFAR. But yes, CIFAR data set is used in driverless cars. Okay. Can I use polynomial to describe the relationship between input and output in supervised learning? Yes, certainly. So polynomial regression allows us to deal with nonlinear data sets. Should it be always 80% of training data and 20% for testing? Well, that's just a rule of thumb. Its figure is not fixed. You could have 80-20 ratio, you could have 70-30 ratio, or even 60-40 ratio. So that is left to the decision of the data scientist. There is no fixed rule. What is the minimum amount of data that is expected for an ML model? Well, typically we like to have millions of samples, right? So it depends on the complexity of the problem and the particular use case. We like to have, lakhs or millions of samples, hopefully. But there are techniques to train machine learning with less amount of data as well. It gets more complicated, but certainly there are some ways to do that. What is the best way to find data on the internet? By the way, if you were to Google machine learning datasets on the internet, you'll find plenty of websites which are providing datasets for us data scientists to use. Okay, for learning machine learning or practicing programs with it. So you'll find plenty of datasets on different websites if you were to Google it. How can I avoid overfitting and underfitting? Well, we just discussed that if we find the data is overfitted, it's not generalizing well to new kinds of data, then we have to send it back for retraining, right? And change something, regularize. There are some certain regularization techniques we'll discuss in future sessions of our webinars, how to regularize and prevent overfitting. In labeled data, what is the difference between test data and validation data? So we already discussed that sometimes we will, for example, a teacher in a class, she may do two exams, not just one final. She may do one more final exam, right? So out of 10 problems, she'll teach 7 problems, keep two for the final exam, and one final problem for the super final exam. So we want to reserve yet more data for a second level of testing. You can call the validation as the second level of testing. By the way, test and evaluation are interchangeably used, but validation is the third or second level of testing. Okay. And what is normalization? Is it same as regularization? No, no, no. So normalization is a technique to prepare your data and normalize it on a certain scale. Because let's say I'm trying to predict, insurance premium. So I have an age of a person and also I have a salary of a person. Now the age might be on a scale of year 10 to year 70, assuming a person can live from year 10 to year 70. But the salary of a person may be in the range, let's say $10,000 per annum to $200,000 per annum. Let's assume. So the two input variables have different ranges. So we normalize them to bring them on the same kind of scale. This is called data normalization technique. It is part of the data preparation step. Okay. Regularization is different. Regularization means techniques to prevent overfitting and creating more generalized models. Okay. We already discussed testing data and evaluation data is pretty similar stuff. Which unsupervised learning algorithm is most suitable for chatbots along with NLP? So for chatbots, mostly we use natural language processing, yes. The speech recognition applications can also use neural networks, okay, NLP, neural networks, and some kinds of classification models. And on what factors do we decide algorithms for chatbots? Well, chatbots are of different kinds, right? So the Amazon Alexa and Echo chatbot are trained using recurrent neural networks, and they are trying to do language modeling with neural networks. But you can also do with regression and classification algorithms. Okay, so there are so many algos which are used in chatbot, not just one particular one. All right, so that was the questions. Now let me show you some tutorials before I address more questions. So I am showing you now the code for linear regression. Okay, let me show you the data set to understand the data set we are dealing with. I'll just increase the font size here slightly. So you can see this is a model which is trying to predict the price of the house based on the area or the square footage of the house. So a house which has 2000 square foot area, the price is $88,600. A house which has 1600 square foot area, the price of the house is $71,600 and so on. So I'm provided this data set. This is my training data, right? And you can see we are provided 40 such rows. So I'm discounting first row, which is the header row. So total 41 rows, but minus the header, there are 40 such rows. And I'm trying to train a linear regression model on this data set. Now let me go to the program. So just let's go through this code quickly. So you can see I'm using something called pandas library. This is a Python code, and I'm using pandas, which is a data manipulation library. And I call this command called read.csv, which reads that CSV file into memory, into this array called flat data. I extract the input x value, which is the square footage of the house, the first column, into the x value, and then the output y is the price of the house, right? and I put that in the variable y. And as you know, we want to split the data into training data and test data. And here we are doing 25%. So the comment actually says 80-20, but actually what I am doing is 75-25, right? So I am keeping 25% or 1/4 of the data for the test step. The test size is 1/4 of the data set. So I create two data sets. One is training data set, X train, Y train, and the second is test data set, X test, Y test. All right. So now I have split the data set provided to me into 75% test data set, training data set, and 25% test data set. And then I train a linear regression model. So Python library called scikit-learn or sklearn gives me a library, a class called linear regression. I can just directly call that class. It gives me a regressor agent. Then I call a fit on it. Dot fit means find the ideal weights for the equation y is equal to wx plus b. And I feed it the training data set. So it trains that model, and then I use that trained agent to predict the output y on the x test part of the test dataset. Notice in this equation here that I am not using y test, right? Y test is a known value. I am only using x test and I am predicting the output y using the trained regressor agent or the trained model. And then I will compare the whether it is predicting correctly or not. I'm just going to plot it out for you. All right, let me just run this and see what happens. So you can see the training data, the green was the training data, right? For area of the flat is on the x-axis, price of the house is on the y-axis. So the green dots represent the training data and the red line represents the trained model, okay? The equation which has been learned by observing this training data. Now what I am going to do, I am going to retrofit this trained line, red line, on the test data and see if it predicts the output correctly. Well, so I overlaid the test data, the 20% or 25% of the data is reserved before, and I overlaid the trained model, which is the red line, on the test data. And you can say, yeah, it is approximately satisfying the test data points. So we could calculate the accuracy of this also, and it might be approximately 80% accurate, because obviously the red line is not passing through all the test samples, the green dots shown here. These are all X test data points from the test data set, the 25% data we reserved in the beginning. But the red line is approximately satisfying the test data, not exactly. So it might be, let's say, 70 to 80% accurate. So it is kind of hard to make it more accurate, because even a polynomial will not satisfy these test data so easily. Linear regression seems to be the best bet here, by the way. So machine learning is an approximate science. So we found a model which is satisfying the test to an approximate degree. Okay. Now let me try a different. Somebody was asking about polynomial regression. Let's see the data set for a polynomial regression model. You can say that I am trying to learn a model where I predict insurance premium for, let's say, life insurance based on the age. So if the age of the person is 25, the insurance premium is $4,500. Whereas if the age of the person is 30, the insurance premium is $5,000. Okay. So there are 10 such data samples given to me. I'll try to train a model which can predict insurance premium based on the age. Okay. Let me just open that file. So there is a Python file here for this particular problem. And let me walk you through the code quickly. So again, I read using pandas. I read the CSV file, insurance.csv. I read the data set into this array called insurance data. I extract the input X and the output Y values from that table which we saw in Microsoft Excel. I train a linear regression. I derive a linear regression model first. Then I also derive a polynomial model. So I create a polynomial regression with degree 2. So if you know what is a polynomial, in algebra, it is a curved line. It looks like a parabola. Okay, so degree 2 means a parabolic line, not a straight line. And then I combine the linear regressor with the polynomial feature. So what is the polynomial feature? X square. So instead of saying y is equal to wx plus b, it would be of the form y is equal to wx square plus b. So that is called polynomial when you square that x value. Instead of wx plus b, it becomes wx square plus b now. And I do a fit and then I plot it. Let's just run it and see what happens. So you can see initially I applied a linear regression on this data set. Now notice the data set was of curvy nature. It was parabolic in nature, right? And it was curved. It was convex shape. But the linear regressor line is not a good fit for the red dots. This is linear regression did not work well. Well, the polynomial looks better, doesn't it? So now I changed the linear regressor into a polynomial regressor. And now it is able to do a better fit than compared to before, right? And this is the equation of this kind of line would be something of the form y is equal to wx square plus b. X square would mean that it would make it parabolic or convex shape in nature. Now also I'm trying to predict using this model for input age 68 what should be the insurance premium. Okay. Now if I use the linear regressor and for age 68 it is saying the insurance premium should be around $58,000. Okay, but this is not correct. The correct value for insurance premium for age 68 is around $74,000. Okay, because that falls more in line with the initial pattern. So as you can see, I tested it with a test, age of age 68. You can see the age x 68 and y printed at the bottom right, and it is predicting the output y for that red dot. So this is a test dot. I am trying my train model in production. I am seeing which models predict the insurance premium correctly. The polynomial regression predicts 74,000, which is more like it. The earlier linear model was predicting wrong value because it was not good fit. It was underfitted. I'll just run it one more time. The linear, as you can see in the output window here, the linear model is predicting 58,000 as the insurance premium for age 68. The input I gave was value 68, the x value is 68, and I was testing which one predicts the premium correctly. And the polynomial prediction $74,000 is more in line with what I expect it to be. I'll run this again just for your understanding sake. So this was linear regression on this data set. This was polynomial regression. This was trying to predict the insurance premium using linear regression. Is not coming very good. If you see in the bottom right, it prints the x and y. But when I use polynomial regressor, it gives me better, more accurate output for age 68. So let me just go back to questions quickly in case anybody has lots of questions probably. Uh, how can we calculate the train error and test error? So we can do compare. So there are some commands within that class which will compare the accuracy. So there are some Python libraries which will compare the accuracy of your train model, and you can print the output. Is it 80% or 90% accurate? I don't have that code here, but there is code to do that. Okay, which is this IDE? I am using something called PyCharm here. It's a popular IDE. It has two versions: Community Edition and Commercial Edition, which is paid. I am using the community version of PyCharm. There are many editors or IDEs for Python programming. You can use PyCharm, you can use Eclipse. Even Microsoft Visual Studio also supports Python programming with a certain plugin. And there is also something called Jupyter Notebook. Okay, so there are many IDEs you can use for Python programming. Okay, let me just go back to show you one or two more models, maybe this time in classification, then we'll be done for the day. So I am now going to show you a classification model. I'll just increase the font size here. You can see I'm trying to predict whether a person will buy a house, yes or no. And the two input variables are age of the person, the estimated salary of the person. So the first two columns are the input x, first feature, second feature. The third column is the output y. Is the person going to buy the house or not? 0 means will not buy. 1 means will buy. So this is historical data given to us, where some of these people bought the house, some of the people didn't buy the house. So using this, we are trying to learn a model where I can predict, given the age and salary of a person, will the person buy the house or not. So this is interesting artificial intelligence. So you are able to predict if the house will even sell or not based on the age and estimated salary of the potential buyer. Okay, let's train a classification model using K nearest neighbor algorithm, which is a popular classification algorithm. I'll quickly go through the code again. I read the homebuyer.csv file. I extract the two input x variables and the output y, and then I split the data into 75% test data, 25% 75% training data, 25% test data. Then I do a fit and transform. Basically, I'm normalizing the data here as we discussed. We'll see more about data preparation and data normalization in one of the subsequent webinars. And then we fit the KNN, K nearest neighbor model. It's called K nearest and K neighbors classifier. And we train a classifier with training data set, and then we predict the output for the X test, the test data set. Okay, and then we also print something called confusion metrics to check the accuracy of my model. Let's just run this. And see what kind of output it shows. So you can see that given the two input features, the age of the person and the salary of the person, x1 and x2, it has now plotted a classifier. So the line between blue and red is the classification boundary. Okay, we call it the classification boundary, and that boundary delineates or segregates uh, folks who bought the house, samples which bought the house, and samples which did not buy the house. So probability of house, the y equal to 1. The right scale shows the probability of the output buying decision. The house y is equal to being 1. 1 means bought the house. So it basically trains a classifier boundary between these two kinds of data samples, those who bought the house and those who didn't buy the house. Once it knows the boundary for any new input sample, it is, if the sample happens to fall in the blue zone, it will say likely to buy the house. If the new input sample happens to fall in the red zone, it will say will not buy the house. So you can try to make a prediction whether a new person will buy the house or not, based on whether that sample falls in the red zone or the blue zone. Okay, so this is how a classification model works. It tries to find what we call the classifier boundary. All right, and confusion matrix, which is printed here, which I am highlighting now, is a technique to print the accuracy. So in the interest of time, I won't take this up right now. It's a long discussion what is a confusion matrix, but this is one way of measuring the accuracy of our model, as somebody was asking. Let me quickly go back to the questions. In regression, how do we handle time dimension? Well, it's like any other factor. If time is a factor, you'll put it as one of the input x variables. Okay, everything is a dimension in machine learning. So if time is a dimension or a feature which matters, you'll just treat it as one more x variable. Like predict the demand for next year winter. Yes, so time would also be a factor if I'm trying to do weather prediction at a certain point in the future. Can we get the code of the example you showed today? Well, this is generally copyrighted. This webinar will be available on a YouTube channel. So unfortunately, we cannot share the code, but you can always see this program running, the exact thing you saw today on a YouTube channel. And if you still need to get access to our content, kindly contact us offline. Okay. So that's all the questions I see today. We are totally out of time. In fact, 9 minutes over. If you have one final question, you can put it in the chat window. Otherwise, I'll have to close this session in interest of time. In regression, how do we handle time dimension? Like predict the demand for next year winter. So the answer to that is, I think I try to answer that. Time is one more variable which will be an input attribute or input feature or input, X value for me. And given that various weather predictions in the past, and so whether it was rainy or cloudy or sunny, so that was the output prediction, and the input would be the other weather conditions like temperature or cloud patterns or pollution levels or the time of the year. Those are all X variables. I'll be able to build a weather prediction model. So friends, I am totally out of time. I appreciate your time and attention this evening, this morning, whatever relevant. Thanks for attending. Kindly look out for our other webinars in the future. Thank you.